Alright, this is the second video on the introduction to chapter 8. We are going to be talking about the motion of a charged particle moving in a magnetic field. We are also going to be talking about the Lorentz force and finally the magnetic force on a current carrying wire. So first thing first, let's talk about the motion of a charged particle in a magnetic field. So we're going to have that diagram over here. We imagine that the particle initially is moving to the right on the board. We have a magnetic field pointing into the board, basically. Now, in this case, in this diagram, we have an electron moving, all right? So we have the velocity in that direction. We curl our finger toward the board, so the magnetic field is pointing inward. The magnetic force will be pointing upward. However, the charge is negative here. And when we have a negative charge, that means it is in the reverse direction. So in this case, the force will be pointing inward. Now note, at all time, the force, velocity, and magnetic field will all be perpendicular to one another. What this means is there's a force pointing downward. That means the particle will start curving in, but as it starts curving in, the force will change. So if we have the electron at this point now, the force will be pointing inward at all time. Well, we've seen in the mechanics semester what that means. This means that the electron will follow a centripetal motion. It will start following a circular motion, all right? Now, there's a couple of important points here. If our velocity and force is perpendicular at all time, that means there's zero work being done on the charged particle. Let's have a look here. So the work done on a particle is equal to the force multiplied by the displacement multiplied by the cosine of the angle between these two. Well, the displacement is always in the same direction as our velocity, so it's in that direction. The force is pointing downward. Both of them are always perpendicular. So there's a cosine 90, work is equal to 0. That's an important point first, all right? The second thing is, well, if it's following a circular motion, it means we can use the centripetal force formula in order to determine the velocity of our charged particle in that force. It can also tell us the radius of curvature depending on the situation. So the centripetal force is equal to the mass of the object or the charged particle multiplied by the velocity square divided by the radius. Now note the radius will be like the center of the circular motion, or in this case, all right? Now, the source of the centripetal force will be the magnetic force. So the magnetic force, the magnitude of the magnetic force is equal to the charge, multiplied by the velocity, multiplied by the magnetic field, sine of the angle between these two, all right? And it is equal to the centripetal force formula. Now, one thing that is worth mentioning is just talking about these concepts are hard to grasp at the beginning. So if you are not sure about all the detail right now, that's fine. These are way easier understood while we are solving some problem, all right? This is just an introduction. It's to get you thinking about these concepts. But if you do not grasp everything, do not freak out. It's completely normal, all right? Let's go to the second concept I want to talk about, which is the Lorentz force. The Lorentz force is simply the magnetic force and the electric force combined, all right? So the force vector, the electric force vector is equal to the force due to the electric field plus the force due to the magnetic field. You will see we will solve some example where we combine both of these concepts. So there's nothing new here. It's just that it is possible to combine both at the same time, an electric and in a magnetic field. And you will see that there are some interesting devices that we're going to talk about that use precisely both to control the velocity of a charged object. All right. Lastly, and last thing about this chapter is we want to talk about the magnetic force applied on current carrying wire. So charge that are moving in a magnetic field, there will be a force on these charge. Well, if there's a current inside a wire, that means there's a lot of charge moving, all right? So the magnetic force is the magnitude of the magnetic force is given by this expression over here that we already talked about, and there's a many steps in the derivation to go from here to here, but both of these are equivalent. So from the point of view of a wire, the magnetic force on the wire is equal to the length of the wire. So that's an important characteristic. We need to know how long it is. Multiplied by the current, multiplied by the magnetic field, multiplied by the sine of the angle between the current and the magnetic field. So for example, in this case, we have the current moving to the right. So we point our finger toward the right, we curl our finger toward the magnetic field, and our thumb pointing out of the board is the direction of the magnetic force. And again, I know I'm repeating myself. Don't freak out. We will do plenty of example to get used to these new concepts. All right. So in the next video, we are going to be starting to tackle some of the problems, starting with practicing the right hand rule. All right. So see you in the next video.